Hey, Vlad here, devinsideyou.com. Welcome to another video. I know I promised you a video about the environment model of computation, but then I realized that it might not even be clearly enough what models of computations are and why they're useful in the first place. This video should help with that. We will try to answer these questions today and provide an overview for the most prominent models of computation. Eventually, I will create videos about all of them and create an entire playlist dedicated to this topic alone, and probably yet another playlist dedicated to the videos related to computer science in general. But something tells me that I shouldn't make any promises about the dates. I have something very special for you today. I'm gonna read out a paraphrased paragraph of a Wikipedia article. It's a biography of a very famous musician, and your job is to guess who that is. I will avoid reading out any names from that article. Okay, here we go. Born in Bonn, the capital of the Electorate of Cologne and part of the Holy Roman Empire, our hero displayed his musical talents at an early age and was taught by his father, so-and-so, and by composer and conductor, so-and-so. At the age of 21, he moved to Vienna, where he began studying composition and gained a reputation as a virtuoso pianist. He lived in Vienna until his death. By his late 20s, his hearing began to deteriorate, and by the last decade of his life, he was almost completely deaf. In 1811, he gave up conducting and performing in public, but continued to compose. Many of his most admired works come from these last 15 years of his life. I'm gonna give you a second to pause the video if you really want to guess who that is, but I guess the hearing loss should have given it away pretty easily. Welcome back. Let me read the answer for you, also from Wikipedia. Ludwig van Beethoven, who lived from 1770 to 1827, was a German composer and pianist, a crucial figure in the transition between the classical and romantic eras in Western art music. He remains one of the most famous and influential of all composers. Now, I mentioned in my previous videos that music plays a big role in my life, but this is not the reason why I brought Mr. Beethoven into a computer science video. Here's the thing, let me recap the most vital part for you again. By the last decade of his life, he was almost completely deaf, and yet, many of his most admired works come from these last 15 years of his life. How did he do it? Think about it. Like, to me, in my head, it sounds like driving a vehicle blindfolded. The next best thing that he could have done was singing without hearing himself. He did it because he knew exactly how each and every instrument would behave. He knew precisely how to write down each and every note so that other musicians know exactly what to play, how to play, when to play. This task required knowledge of music theory, technical skills in as many instruments as he could get his hands on, precise memories of the sounds those instruments can make, and at the very least a unified notation for those notes. All of this combined is a model for music, and this video is about models of computation. Now, the whole Beethoven metaphor was my attempt to explain to you what models really are, in general, not only models of computation. Before allowing me to even attempt to formally define what models are, we should be asking ourselves a very valid question. Why should we care? Here's the thing, not every musician has to be capable of what Beethoven was capable of, but I'm sure as hell that each and every one of them dreams to be as capable as Beethoven was. Unfortunately, somehow it's not the same for programmers. I don't really know why that is so. Maybe it's because the majority of programmers is relatively young, or maybe it's because in addition to that, the majority of programmers is also relatively male. And yes, pun intended. I don't know why we're so eager to leave the science part out of computer science, but with this video I will try to put the science back in programming, and I can only hope that you're still here with me and you don't allow some cat videos to steal your attention. Now I see that you started thinking about cats. Now stop thinking about cats. Stop it! Alright, so what is a model? I found quite a few definitions on the web. There are different models for different things. Let me read out a few of them for you. A math model, for instance. A math model may help to explain a system and to study the effects of different components and to make predictions about behavior. Well, okay, I like the part about predictions about behavior, and there's also something about different components. Okay, let's take another one. A conceptual model. A conceptual model is a representation of a system made of the composition of concepts, which are used to help people know, understand, or simulate a subject the model represents. Okay, so a model seems to be a representation of something, and the part about different components seems to be paraphrased to composition of concepts. I very much like the part about helping people know and understand the subject the model represents. Alright, cool. The last one on the menu. A mental model. my favorite one. A mental model is an explanation of someone's thought process about how something works in the real world. It is a representation of the surrounding world, the relationships between its various parts, and a person's intuitive perception about his or her own acts and their consequences. Mental models can help shape behavior and set an approach to solving problems and doing tasks, similar to a personal algorithm. Okay, firstly, I obviously love the fact that they use the word algorithm. It's just cool, period. And we see the similarities again. First, we had predictions about behavior. Then we had the part about helping people know and understand the subject. And now we have an explanation of someone's thought process and even a person's intuitive perception about his or her own acts. So what about models of computation? What are they? Well, I guess any combination of the things that I just read out will do. A model of computation will hopefully help us predict the behavior of our programs. It will hopefully help our teammates to know and understand a subject represented by our programs, and how awesome would it be if it could also explain the thought process of a programmer or provide an intuition about the actions of a program or a programming language. And here's a long-awaited formal definition from the single source of truth, Wikipedia. In computer science, and more specifically in computability theory and computational complexity theory, a model of computation is a model which describes how a set of outputs are computed given a set of inputs. This model describes how units of computations, memories, and communications are organized. Look at the definitions again and notice how the word describes is used twice. And I in particular don't believe that this was a coincidence. The first time it is used for the part about how a set of outputs are computed given a set of inputs, and the second time it is used for the part about how the units of computations and other things are organized. So simplified, how do we compute stuff and how do we organize procedures if we happen to have a lot of them, presumably in a very large software system? Let's get a bit more concrete. There are many different models of computations out there that specialize in different things. However, there are only very few prominent ones, the ones that you should know about, and I made a few slides for you. Before diving into them though, let me say one more thing. There's also another thing called programming paradigms, and yet another thing called programming styles, and yet another thing called programming notation. Now, they sort of go hand in hand with models of computation, but they're not the same thing, and we will discuss all of them in the future videos. Alright, let's get to the slides with the models, but as I already mentioned in the beginning of this video, I'm not gonna dive in detail into each individual one of them, so some parts might be unclear, and I hope it will become more clear in the next videos. My hope here is to draw the big picture for you. Let's start from the top, the substitution model. Its full name is the Substitution Model for Procedure Application, and judging by its name, it's there to help us think about procedure application. Or speaking more formally, it is there to describe how a set of outputs is computed based on a set of inputs. It describes how primitive procedures and primitive data structures are combined to construct compound entities. It also allows creation of abstract programs as a means of dealing with the complexity of large systems. The value this model provides is vital for programming. However, software development also requires organizational principles to help guide the overall design of large systems. There are two prominent organizational strategies that are fundamentally different from each other. More about that in a second. One is built on the applicative order evaluation, which means that the arguments to the procedure are evaluated first, and only afterwards are the procedures that are called inside of this procedure are evaluated. More about that in the next video. In fact, we're going to reuse the same slides over there as well. It is called the environment model of evaluation, and at the very first glance, it seems to be very intuitive, which is one of the reasons why it was, and in fact it still is, dominating the entire software industry. It concentrates on the notion of objects, which act as an environment for state variables. The idea is that for every object in the system that we're building the model for, we also construct a corresponding computation object. And for each system action, something that the object does in the real life, we define a procedure. So we have a one-to-one mapping, object to object, action to procedure. The other organizational strategy is built upon the normal order evaluation, which means that the sub-procedures are expanded first, and only then are the arguments to the procedure evaluated. In other words, the arguments are not evaluated to the very last moment when they're actually needed. More about that in the next video. It is called stream processing, and it concerns itself with the information flow in the entire system. And the easiest way to imagine this, and it's also the most popular example, is to imagine a bank account. In the environment model of evaluation, you will have a variable that would represent the state of your account, and every time your balance changes, this state variable changes as well. However, in the streaming model of computation, you will have a constant with the initial value of your account, your initial balance, and a constant is a variable that cannot be reassigned another value later. And instead, you will keep track of a potentially infinite stream of transactions. For instance, if you wanted to deposit $10, you would add a +5 to the stream of transactions. And if you wanted to withdraw, say, $5, you would add a -5 to the stream of transactions. So if you wanted to see the state of your bank account, your balance, what you would need to do is you would need to go through the entire stream of transactions from the very beginning and add them all together. So the state of your bank account is not being tracked per se, but it is always there, hidden somewhere in the flow of information, ready to be computed. The stream processing model is a very interesting one, and we'll have a lot of videos about it for sure. Unfortunately, probably not anytime soon. So to recap, the substitution model concerns itself with the meaning of procedure application. What does it mean to apply a procedure to its arguments? And these two are concentrated on organizing or structuring an entire application. And by the way, people are still arguing which one is the best, but to be honest, they both have their strengths and weaknesses. In fact, blending them is an area of active research. They have almost diametrically opposed views on how they deal with time, which is evident by the dependence on the order of evaluation. And guys, I understand that this is a very abstract topic and some things might not be clear. I hope that they will be a little bit more clear in the next video, which will be concentrated on the substitution model of computation and the environment model of computation. And I know I promised that before already, but this time I'm pretty confident. Now we're almost at the end of the video. I just want to say a few more things. Firstly, this is not the complete picture. This is. Yes, shit just got real. The lower ones are concentrated on concurrency, a notion of parallel computations potentially competing for the same resources. Think about sharing a bank account with your entire family, for example. But I didn't want to go deeper into them because the video is already getting kind of long, and also I didn't want to confuse you guys too much. Secondly, the content in this video is largely based on the book called Structure and Interpretation of Computer Programs, or short SICP. Link is down in the description. It is a free book and it is considered to be the Bible of functional programming. And if it was up to me, I would actually consider it the Bible of programming in general, because I actually read it, okay? It's a very long book, but it is not biased towards functional programming in any way. This book is written by professors at MIT and is based on a computer science course that they taught there, an introductory course, by the way. They wrote a programming language called Scheme, a dialect of Lisp, and in this book they teach you how to build it from scratch, or for that matter how to build any language from scratch. This book sort of as a byproduct teaches you computer science, and as a byproduct of that it teaches you programming. This is also one of the reasons why the book is so much concerned with models of computation. They are very important when you want to write an interpreter or a compiler for a programming language. This book is amazing, and even though it's very, very long, I'm glad that I read it. However, I can't recommend you to read it before you have a few years of programming experience under your belt. The biggest problem that I have with this book is that it is almost entirely written in the domain of math. And by that I mean that almost all examples are examples from math. So when I was reading it and, I wanted to learn programming, I felt that I was also learning math at the same time. And I believe for a beginner, it's a bit too much. Okay, so this video is not about the review of this book, but if you're serious about software development, that I highly recommend that you put it on your presumably very long reading list. All right, we're done for today. A bit of theory never hurt anyone, has it? It's been Vlad. Subscribe if you want to improve the developer inside you. Cheers. Take care.